So I noticed you all were asking questions and not really sure on what was going on. So I decided to just make a quick video, hopefully explaining everything that went over in the beginning of lab and what to do for the lab report, how to do the calculations, all those deviations, and what to do with the peak numbers and all that. So hopefully this will clear everything up, and this will just go along with the graphs I send you guys. So the first thing we went over was Reinberg's equation. And his equation was to predict the amount of energy a photon would be emitted or absorbed into when doing an electron level jump. So we're going to be going over a jump from 2 to 5. So it's going from 2 up to 5, alright? So remember this whole thing? Anyway, so we want to find out this area and how much energy goes on in there. So the equation is 1 over wavelength. And when we find wavelength, we could later plug it in to find energy if we want to. So we're going to find wavelength. So 1 over lambda equals Reinberg's constant, which is 1.0974 times 10 to the 7th times the absolute value of 1 over n squared of the initial minus 1 over n squared of the final. And the initial is always going to be the one you're returning to, or the one you're coming from. So in this case we're coming from the 2. So when we plug it in, we're going to have r times the absolute value of 1 over 2 squared minus 1 over 5 squared. And then that's going to equal this big old number once we multiply it by r, because it's this huge 10 to the 7th. And then that'll equal 1 over lambda. And so if you do a little algebra, bring lambda up, then divide this down, it'll be like this. And just people are having trouble calculating it, so I'm going to show you how it works on the calculator and what to do from there. So hopefully you can see this. So what goes through is I do 1 divided by 2 squared, which is 4, minus 1 over 5 squared, 25, and see what that equals. Then multiply it by Reinberg's constant. I have it entered in my calculator as r, or you can plug it in. And so it's a really big number. And then the way to get it so it's 1 divided by, just press 1, divide, and go up and hit second, and then down here at the bottom, press answer. And there you should get your wavelength. And it's in wavelength form, 4.33 to the negative 7. If we move that over, we can make it 433 to the negative 9th, which is really nanometers, since nanometers is to the negative 9th. And so that's how you're going to calculate wavelength and go from there using Reinberg's equation. So that's basically all was going on there. So the first part of the lab that we did and that we need to talk about deals with the helium lamps and the hydrogen lamps that we were measuring their peaks and everything. So at the beginning, when Ali was asking everyone, what's this next jump? What's this next jump? Blah 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 blah. Those were theoretical things that you were using Reinberg's equations to guess the wavelength. So for helium, which is the first lamp we did, when we did it and plugged it into the Logger Pro, we saw we had many peaks, and so we recorded all those peaks. And if you guys need them, I'll write them down or type them out for you. Anyway, so these are all the peaks. We don't really need to worry about the intensity level, which is over here. It's not really important at the time. And so what I've gone ahead and done is written down the theoretical numbers. And these are all found online on the lab presentation if you need to get these. And so these are all the calculated according to Reinberg's equations wavelengths, lambda values. So this first part is to test whether or not Rydberg's equation, Rydberg, however you spell it, is valid. And the way you test anything with validity is you find if there's big deviations. If there's too big of deviations, it's not really valid. So you calculate all these, or look them all up, and then you're going to compare them to what we read directly off the graph. Because what we read directly off the graph is the actual thing. That's perfect. Theoretical, we're hoping works. That's why it's theoretical. So the way to find deviations is using absolute value of experimental minus theoretical divided by theoretical, then multiply it by 100. So if we wanted to find the deviation for the first part, we'll take 568.8 and we'll subtract the theoretical, which is 587.6, and divide it all by 587.6, absolute value, and then multiply by 100. Plugging that into the equation, into the calculator, you're going to get about 0.13%. So it's pretty close to 0, which is what we want. And so 0.03%, that means there's just a tiny bit of deviation from the theoretical with the experimental. And so you'll go ahead and do that for your own, so you get all these different deviations in percent forms. They should all be close to 1. And you'll see like this one's 0.01, so that's really close, meaning Rydberg's equation held out really strong. So for the most part, Rydberg's equation works well, and that's what we're supposed to prove, that through this validity test, we can test that Rydberg's equation worked out well for all this. Hydrogen's requires a little more work because the theoreticals aren't given to us on D2L or the lab presentations or from Ali. So you're going to need to calculate your own theoreticals, and we wrote down the 3 peaks from the experimental when we plugged in hydrogen lamp. And so I'm not going to explain how I got the gap numbers, but so you're going to use Rydberg's equations to find these 3 numbers. Don't just copy them off of here. So the jumps of electron levels, the first one is 3 to 2, 4 to 2, and then 5 to 2. So plug those into Rydberg's equation, find out what they equal, and you'll get some lambda max value. You'll compare it to the values of the experimental, and you'll get some deviations like I did down here. So I'll just go over one of these just to make sure. So 3 to 2. So the way to remember, it's kind of always just trying to figure out which one is initial, which one is final for the ends. Always do the lowest one for initial. It's easier. So 3 to 2 down here. 3 to 2 is going to be Rydberg's times 1 over 2 squared minus 1 over 9 squared. So I just wanted to show that 2 is always going to go first most of the time. So 3 2, 4 to 2, 5 2, then find out what your theoreticals are, and then find the deviations. So that's for the first part of the mini lab. Oh, short lab. The next part is with the identifying. So at first we did all these knowns, and I don't know if you guys have written these down or if you did or did not. But what I did was I wrote down all the peak numbers for the knowns. And you'll remember that some of them have just 1 peak. These all had just a couple. Or then the other few had big multiple, like, I don't know how you describe them, like 1 peak, then weird looking things like that. You'll see them, I attached them in the email. You'll have all the known graphs, all the sparkler graphs, all the unknown graphs, so you can look at all those. So I wrote down the peaks, and which I will write down. If you can't see them from here, I'll type them out so they're written cleanly. I use this annotation a few times. DP is for double peak. It's nothing really, I just kind of made it up my own, because you'll see on on yeah, on potassium, barium, strontium, and a lot of the unknowns and the sparklers, that there was a large peak near the end of the spectrum, if you remember those at all, and it looked like just one giant peak. However, with closer inspection and zooming in, it actually turns out to be something like this with two multiple peaks. Usually zoomed out, it looks just like this, but really zoomed in, it looks like that. So I called it a double peak, and it happens from at what happens at 766. Ooh, at 766 nanometers and 770. So that's the double peak. So those are all the knowns, and this is our reference table that we have made and collaborated to use for identification later. So I continued and did the same with the unknowns. Unknown A had a good amount, so you can already tell just from looking at that it definitely is probably going to be one of these three, since it has quite a few. And then unknown B and unknown C, and you'll see that all three of them have the double peak, which is kind of interesting. So maybe they all have potassium or one of the main ones in there. Anyway, that's kind of for you to analyze. If not, you can ask me and we could go over that some more. Sparklers, same deal. Sparkler gold had one middle peak and then the double peak. Green had this, red had a bunch. There you go. So what we want to talk about mainly, it's a short lab, remember, it's only going to be 4 pages, is make sure to include the use of Reinberg's, how you found that, how you found the experimental, or how you found the theoretical values over here. Excuse me. And just to make sure I've already had this all checked over by Allie, so I know we're always worried about screwing up. So it's all looking good so far. And I'm going to send you all the graphs. I have all the graphs. They're all on 3 different Word documents. One for the knowns, one for the sparklers, one for the unknowns. And I think that's about it for now. Shouldn't be too much work from there on out. And I'm just trying to get a good jump on this. If you guys have any more questions, just email me back and we'll see what we need to go from there. Alright, thanks.